ARC tutor for Computer Science 1 this semester, and I guess I'm going to be the person that's going to onslaught your brain with some computer science stuff today. With a show of hands, how many of your tests are cumulative? Okay, so a little bit, about half. I guess I'm gonna start. I don't know how many of you have downloaded my review guide, but I'm gonna start towards the end in that case. After that page that says this page intentionally left blank, we're gonna start with like binary search trees and stuff like that. Because that's probably what's more likely to be on some of these people that don't have cumulative tests. Also, if you have questions, please hold them till the end unless they're like egregious mistakes on my part, in which case please let me know because I'm not perfect and I might have made a mistake. Just let me know if that happens. So we're going to start with that first question. It asks, what is a tree? What is a binary tree? Yada, yada, yada. So a tree is basically a graph that has one source dividing into multiple other paths. And this doesn't necessarily have to be binary. A tree can be trinary or quaternary. You can have any number of children. And the ordering is the same thing. It doesn't really matter. We can have any ordering we like. Doesn't have to be in order. So that's what a tree is. A binary tree is a tree where every parent has at most 2 children, but not necessarily 2 children. So this would be a valid binary tree. A binary search tree is one which has that ordering property. Where everything to the left of the parent node is less than that node, and everything to the right of that parent node is greater than that parent node. So the next question is, when do we say a BST is self-balancing? And that basically means that the binary search tree never gets, its heights are never, there's never a difference in height that's more than 2, basically. So we would say that a binary tree that looks kind of like this is definitely unbalanced. But if it's self-balancing, it would take those nodes and move them such that the heights are about the same. And the way we do that is different depending on the balancing algorithm that we choose to use, but you guys have used the AVL outbalancing, so I'm going to go over that. There's a question in here that asks you to make an AVL tree, so we'll look at the algorithm when we get to that. So the best and worst case insertion into a binary search tree is dependent on that balancing. If a binary search tree is balanced, then we say that the maximum depth that we have to go to insert a node into this tree is the height of the tree. So if we have, let's say, 1, 2, 3, 4, 5, 6, 7, let's say we have 7 nodes, the max depth that we have to go to insert another node into that tree is the log base 2 of 7, about. So this is about 3. So we need to go down about 3 steps in order to insert another node into this tree. That's the average case for insertion with a, that's actually the best average and worst case for insertion with a balancing tree. Now for an unbalanced tree, like I drew before, what can happen is you can get something like this. And let's say that we want to insert something that is greater than this node. So let's say that this node contains something like 50, and we want to insert 55. Then it's going to take, we see we have n equals 5 nodes. It's going to take 5 steps to get down to that node so that we can insert to 55. Which we would say is order n. However, with this same tree, we could say that we want to insert something that's less than this, and that's an order 1 operation, because all we have to do is go to the left of this and insert there. Now, something that you guys might have learned this semester is that when we're doing algorithm analysis, that we think of the data structure as being something we call arbitrarily large, which just means that it's large enough for the algorithm that we're using that we can get some kind of timing out of it that's actually reasonable. Because if we say something like this tree is empty and we insert a node, then that insertion is technically inserting 1 node into the tree. So you'd say, okay, well maybe that's an order 1 operation, right? But we only have 1 node in the tree, so our n is equal to 1, and it took 1 step to insert. So this is still an order n operation. So don't fall into that trap. When we do algorithm analysis for generalized algorithms, like inserting into a binary search tree, always think of that tree as having an arbitrarily large amount of nodes already in it. All right, the next question is, when do we say a tree is full? And a full tree is a tree that looks like this, where all of the nodes on the lowest height are all completely filled up. None of the leaf nodes have any more children on that last height. A complete binary search tree, or complete tree, is one in which the nodes on the lowest height are not necessarily filled up, but they're filled up from left to right. So there's no nodes below this last height, this height of, we'll call this 2. There's no nodes below this, so this wouldn't be a complete tree. But this would be, because these 2 nodes are filled from left to right. And you can also say that a full tree is also a complete tree, because all of those nodes have been filled in from left to right. All right, so we're going to do the insertions for a binary search tree that's not self-balancing. I'm going to put the operations that we're going to be doing here. And I think these will cover most of the situations that you'll see in a binary search tree when you're inserting and deleting. But I don't think it covers all of them. I think there's one more deletion situation that you can get into. And I think we'll cover all of the insertions. When we do AVL trees later, you'll probably see the other types of insertions that we have with AVL trees. All right, so 26 becomes the root. 30 goes to the right because it's greater than 26. 15 goes to the left of 26 because it's less than 26. 22 goes to the right of 15 because it's less than 26 and greater than 15. And then we're going to delete 15. And 15 has only one child. So when we only have one child, what we do is we just pick that child up and put it where the parent was. So we're going to get rid of 15, and we're going to pull 22 up and basically just put it where 15 was. Then we're going to keep inserting. So we're going to insert 36, which is greater than 26, greater than 30. Then we're going to insert 20, which is less than 26, less than 22. Then we're going to insert 23, less than 26, greater than 22. Then we're going to insert 14, which is less than 26, less than 22, less than 20. Then we're going to delete 22, and you can see this one has two children. So when we delete it, what we do then is we take the largest value in the left subtree, or the smallest value in the right subtree, and we basically pick that up and put it where it was. And all of its nodes, all of its children, are going to follow it. So we're going to pick 20 up, put it where that was, and 14 follows it. And I already deleted it, but 22 would go down here. Well, not down there. You would replace it down here, and then you would delete it. And it has no children, so it just goes away. So that is the final binary search tree. And I also asked you guys to give the pre-order, in-order, and post-order traversals of this tree. So the final tree, I'm going to go ahead and do the pre-order, in-order, and post-order of it. Basically, those traversals are what they sound like. So pre-order means print before we traverse, in-order means traverse left, then print, and post-order means traverse left and right, then print. So pre-order, we're going to say 26, then we're going to traverse left, 20, we're going to traverse left, it's 14, then we're going to return, then we're going to traverse right, 23, then we're going to return, traverse right, 30. We'll try to traverse left, but we can't. Then we'll traverse right, 36. So that is the pre-order. The in order is, remember, the one where we traverse left, then we print. So we're going to do 26, 20, 14, and we're going to try to traverse left, but we can't, so we'll come back, and 14 is going to be the first thing to print. Then we'll go back, and then, well, we'll try to traverse right, and then we'll come back. And then we've already gone left, so we'll print 20 out. Then we'll go right, and we'll try to go left, but we can't. Then we'll come back to 23, print 23 out. Try to go right, can't. Come back up to 20, come back up to 26, and then we've gone left, so we'll print 26. Then we'll go right to 30, try to go left, but we can't, so we'll come back up to 30, print that out. Then we'll go right, see 36, try to go left, but we can't, so we'll come back to 36, and we'll print that out. And notice how the in order will always be actually in order. So no matter what data you're storing in this binary search tree, it'll always look, no matter what you have in the binary search tree, that data will always be in order. sorted order. All right. So the last one, post order, is the one where we go left, then right, then we print out. So we're going to go 26, left, 20, left, 14. Then we're going to try to go left, we're going to try to go right, and we're going to print 14 out. Then we're going to come back, we're going to see 20, but we're not going to print it out yet. We're going to go right to 23, try to go left, try to go right. We're going to come back to 23. And then we're going to come back to 20, and then finally print that out. Then we'll go to 26, and try to go right on 26. Then we'll go left on 30, and then we'll try to go right on 30, which we can. So we'll go to 36, and we'll try to go left, we'll try to go right. We'll come back to 36, then we'll come back to 30, then we'll come back to 26. So that's what the post order would look like. All right, so we're about to go to AVL trees. Is everybody good with binary search trees right now? Any questions? Binary search trees aren't too bad. Just try to remember those different deletion situations where you take the maximum in the left subtree. It's probably the most difficult thing on binary search trees. AVL trees are a little bit more difficult, as you guys might have encountered in your classes. I'm going to write out the different types of rotations in the top left so that you guys can refer to them. If you have a left-left, then we need to rotate right once. If we have a left-right insertion, then we need to rotate left once, then right once. If we have a right-left insertion, then we need to rotate right once, then left once. And if we have a right-right insertion, then we need to rotate left once. So as we're inserting into this tree, I think you guys will see one double rotation and one single rotation. All right, so I'm just going to insert these because we already did binary search trees, so you should probably know where these go. 30, and then at every point in an AVL tree, we're going to check the heights. So I'm not going to do it for every step, but you would check the balance factor all the way up to the root node after you inserted this 30. So we'd start at the 30, we'd look at its balance factor, which the balance factor of an empty node is, or the height of an empty node is -1. And so we would do -1 minus -1, which is just 0. The height of a leaf node is always, or the balance factor of a leaf node is always 0. So the balance factor here is 0. The balance factor here would be 0 versus -1, which means the balance factor is just -1, or actually it's +1 if you do left minus right. But a balance factor of 1 is fine. Nothing needs to be done with a balance factor of 1. The problem occurs when we have a balance factor of either 2 or -2. So we're going to keep inserting until we see one of those conditions where the balance factor is 2 or -2. Now, the next one is 52, then 36, and then 40. And now we should have a problem. So it's kind of easy for me to see, but, and as you guys do it more often, you'll be able to see balance factors pretty easily. But it's pretty obvious that at 30, the left here has a -1, and the right here has a height of 2. Well, actually, 1. The right subtree has a height of 1. So here, we would have a balance factor of -1 minus 1 equals -2, which is a problem. So now we need to fix that problem. And this rotation is going to be what type of rotation? Does anybody want to say? single left rotation because we've inserted to the right. So we kind of say that this is right heavy because the balance factor here is -2. So that's where we found the imbalance, so it's right heavy. And then we go to the right and we see, okay, well, what's the balance factor here? So the balance factor here is -1, which tells us that it's right leaning. And when it's right leaning, that tells us the kind of rotation that we want to do. So if it's a single rotation left, then we do that rotation around the node that has the imbalance. So what we're going to do with this single left rotation is we're going to basically pull 36 up to where 30 is, and 30 is going to fall down basically on the left-hand side, and 40 is going to fall down on the right-hand side. So it's kind of like pulling up beads. You might have heard that analogy before. You're just going to pull that 36 up, and everything else to the left and to the right is going to fall down into place. All right, so everything just falls down into place, and you'll see that the ordering property is kept. Everything to the left of 36 is less than it, everything to the right is greater than it, and same with 46, everything to the left is less than it, everything to the right is greater. So everything's good. The balance factors of everything are fine. If we look at 46, then the balance factor would be a 1 on this side versus a 0 on this side, so the balance factor is just a 1, which is fine. So now we're going to keep inserting. So the last thing we inserted was 40. Now we're going to insert 58. And then 44. And we should still be good here. Then 32. And then 41. Oops. Now, I haven't been checking the balance factors all this time, but I kind of want you guys to see like what imbalances look like rather than having to calculate the balance factor at every single step, because for the test you're not going to want to go through and check the balance factor of every single node. You know how to do it if you have to, if you forget how to just see it. So if you need to, you can calculate the balance factor, look at the left subtree, look at the right subtree, calculate the heights, and then calculate the balance factor. But this is an imbalance, and this is an imbalance that is right-left, because the imbalance is at 40. The left has a height of -1, and the right has a height of 1. So -1 minus 1 is -2. So we have that same type of imbalance where it's -2, so we know it's right heavy, right? But we don't know what type of leaning we're seeing here. So we're going to go to 44, and we're going to calculate the balance factor of 44. And we're going to look left, and we're going to see a 0. The height of 41 is 0, has no children. And the left, on the right, we're going to see it's empty, so that's a height of -1. We do 0 minus -1, and we see a 1, which means that it's left leaning, which means that we have a right-left insertion, basically. And with that right-left insertion, a little cheat sheet, we need to do 1 right rotation and 1 left rotation. So the right rotation is going to happen around that middle node that was leaning, and then the left rotation is going to happen around the top node that had the imbalance. This is how double rotations always work. We do the first rotation around the one that had the leaning problem, and then we do the other rotation around the one that had the imbalance problem. So if we rotate 44 right, it's that same thing. We're going to pull 41 up, the thing that was to the left, and 44 is going to fall to the right, and whatever was to the left of 41 is going to fall to the left, but there's nothing there, so it's just going to jump up there. And now we're going to see this. And if you look at this, this looks like the situation where we had a single left rotation, right? Which is why we do those double rotations, because that first rotation is going to get us into one of those conditions where we could do one single rotation and get it working. And that's the reason this works. So we're going to rotate this thing left around 40. So we're going to pull 41 up, and 40 is going to fall down to the left. 44 is going to fall down to the right, just like the beads analogy. And we'll see that we have no more imbalance. Now, some of you might have been concerned about the 46 during all of this, because it also had an imbalance. And that will always be true. When you have an imbalance that's further down in the tree, you'll always also have imbalances further up in the tree, which is why we search up from the root or the leaf node that we inserted. All right, so the next insertion is going to be 30. It's going to be 41. Oh, we already did 41. It's going to be 22. So 22 is going to go here. Then 34. It's going to go here. Now, there's an imbalance. Does anybody know where it is? What node the imbalance is at? This one's a little bit more difficult to see, so I don't blame any of you. If we calculate the bounce factor all the way up, what we would see is the bounce factor of 32 is fine, 30 is fine, 36 is fine, but once we get up to 46, we're going to look at the left, and the maximum height on the left is going to be 1, 2, 3, 4. And the maximum height on the left, or the right, is going to be 1. Actually, that should have been 3, counted from 1. But either way, if we calculate, the bounce factor is going to be 2. So we have an imbalance, and it's around 46. Now, this imbalance looks really scary because it looks like we need to take care of like a lot of nodes and stuff. It's not. The most things that you'll ever have to keep track of is like 4 nodes, and I think this is like the worst type of rotation you'll ever have to deal with. So we're going to look at it, and we're going to go to the left because that's the imbalance. The imbalance is to the left because it was positive 2. And we're going to look at where it's leaning. So 36 is going to have a bounce factor of 0, 1, 2, minus 0, 1. So it's going to be leaning left as well, which means that we need to do a single right rotation, and that should get this balance. So I'm going to redraw this tree and try to do it over here. Okay. But basically what's going to happen here is 36 is going to come up. 36's right child is going to get orphaned because 36 can't take 2 children. So it's going to take 46 as its right child. 41's going to get orphaned for the time being. We're not going to worry about that. We'll tell you about that later. And then 30 is still going to stay where it's at. So the only thing we're worried about is this 41. That's going to get kind of dropped for a bit. And then we'll come back and I'll show you how to fix that. All right, so this is basically the entire tree. I think you can see all of it, except for that 41, 40, and 44. Now, 41 got orphaned because 36 couldn't take any more right children. They had to take 46 as its right child. But 41 can fit somewhere else in the tree. Where is that? Anybody can tell me? What is that? The 46? Yeah, so the left of 46. This 41 can still fit in there. And so we put it in there. It's kind of a messy tree, but it is balanced, trust me. So we inserted 34, that's what caused the imbalance. So now I'm going to do some deletions, which are going to cause some problems. So when you delete from a AVL tree, you're basically going to do the binary search tree fix. And then after you do the binary search tree fix, you're going to check for imbalances. So I've put delete 36 on here, so we're going to delete the 36 node. And just like we did with the binary search tree, we're going to take the largest element in the left subtree, and we're going to put that where that 36 was. So that's going to be 34. So now we have this tree. And if we check where that thing was swapped, that would be where the imbalance would occur. So if we check from here, we can check and we can see this thing is still balanced, we're still good. Now we're going to delete 58, which is over here. And we can just delete a leaf node, that's fine. The leaf node has no children, so we're not worried about it. But we do need to check up from that leaf node to see if there's any imbalances now. So we'll look, 52 is fine, 46 is fine, 34 is also fine. So now we're going to delete one more thing, and this should cause an imbalance. So I'm going to delete 52. And by deleting 52, I've caused an imbalance. Now that we've gone over a few of them, can anybody tell me what node is imbalanced? Yeah, 46 is imbalanced right now. So if we look at 46, it's pretty easy to tell because it doesn't have any right children. It's left leaning, and well, it's left heavy, and if we calculate this balance factor, then it's just neutral. So we're not going to worry about that right now. So what we need to do here, we could rotate either way really, but I'm just going to do a single right rotation because it works out better. So if we do a single right rotation here, then we'll have 41, 46, 44, and then 40. And like I said, you could really choose to do the double rotation or the single rotation there. It doesn't really matter. The only time that's going to happen is when you have deletions. And it's kind of just a matter of choosing like how you want to deal with it. But the single right rotation is probably the easiest way to deal with that problem. When you have a neutral balance factor, you can really choose whichever one to do. All right. So that is that for AVL trees. Does anybody, okay, one more thing for AVL trees. AVL trees, I think I might have said it before, self-balancing trees in general always have an insertion and, always have an insertion of login, and a deletion is, we also say it's login. You might say there's a few more operations to do, like doing the rotations and stuff, but that still comes out to be login. All right. So any questions with AVL trees? Good. All right. So now we're going to move on to tries, which I think all of you have done tries or should have. But basically, tries are trees that hold strings in them, and they're very efficient for lookup of strings. So I asked, what does the trie node struct look like? There's a few different ways to keep control of a trie. I'm going to say that this one is going to keep count, but this can also be a flag. This thing here tells us whether that word is in our trie. And then we have an array of 26 trie nodes. And this is what keeps track of the string. So as opposed to binary search trees and heaps and stuff like that, where the data is stored within the struct, this one is the data is stored within the path that you take with the struct. So the actual data in here doesn't tell you anything about where to go. It just tells you that this word is in here, basically. So I asked you to insert a few words into a trie, and inserting into a trie is pretty easy. Deleting from a trie, I'll also show you guys some deletion from tries, but that's also pretty easy. The most difficult thing that you guys probably see with tries is a runtime question, or possibly something that implements tries in some like larger algorithm. I wouldn't. Okay, so these words are on my sheet. I'm not going to write all of them out. I'm just going to insert them into the trie. And I have a few others in there, but I think I'll stop there because I think that's enough. But you can see that the path is basically what you take. And so I inserted Muffin, Mulligan, and Mufasa into this one. And this M and this C are part of the what we might call the head of the trie. So this is stored inside of the actual like trie that will pass to functions to like search through it and stuff. So this is the initial array. And then basically all of these are just parts of that trie node. So that trie node has 26 other trie nodes within it. And we only have one that's actually got anything in it, just the U. And the way we can tell that that's there is because this wouldn't be null. If we checked it, this wouldn't be null. So we'll see, okay, we'll go to U. And let's say we're looking for Mulligan in here. We'll go left to L all the way down here. And what we'll see down here is that that count will equal 1 on the N. And then if we want to like print this out or something, we'll check, okay, well this is set equal to 1, so we know that word's in there. We'll be keeping this word in a buffer the entire time, basically. And then we'll print it out after we reach that 1. Now if we want to delete from a trie, let's say we want to delete Mufasa from this trie. Now, we might start at this A here and say, okay, well we can delete this trie node because there's no other children. And I'll go up to S, and even though we deleted that A because I had no other children, we can't just delete S because S might lead to other places. You'll see that in a second. So we'll delete S because it doesn't have any children, but we'd have to go through that entire 26 trie nodes and see none of these have children before we delete it. We'll look at A and we'll see it has no children, and so we'll delete that. And we'll look at F, and we'll go through all of the trie nodes, and then we'll see it has an F child, so we'll stop deleting because there's other words there that are still down that other path. So now we've deleted Mufasa from here. but all of the others are still in there. And when you delete, you might choose to actually delete the nodes like that, or you might just choose to set that flag equal to 0 to basically say this word's not in there anymore, depending on how you want to do it. One way is more space efficient, one way is more runtime efficient. That's basically tries. If you have other questions on tries, I can do some more later. But I have some runtimes on here. So I asked what the worst, average, and best case runtimes for insertions, deletions from a trie are. Yeah, what's the question? Not sure. Yeah, it kind of depends on what you're trying to do. I think that the best way to do it is to delete everything. So like, when I deleted Mufasa, I would say that the way I did it first is the best way to do it, to free those nodes as you're going up, because then you're getting rid of that space. And it kind of depends. If you think that you're going to see that word again, so like let's say you're reading it from a dictionary or something, or some kind of like document, if you think you're going to see that word again, let's say you decremented it at some point, let's say you're going to see it again and you want to like turn it on, it's more efficient in that case to keep it and just decrement the flag, because you don't have to create that memory again, which is more time. So it kind of depends. If you think you're going to continually see words repeating and you decrement that flag and you think you're going to see them again, keep it there and just decrement the flag. If you think that you're only going to see words once and then basically never see them again, and you're just going to delete them as you go, then I would get rid of that memory because you're not going to need it. It's kind of the same thing with any data structure. You can delete stuff, just get rid of it if you're never going to see it again. Otherwise, you might want to keep it around and just turn off any flags that you might have for it. All right, so did that clear up your question? You're welcome. So I had some runtime questions on here, like I was saying. The worst, average, and best case insertion, deletion from a trie. There's only like a couple of tricks here. Best case and worst case insertion is always going to be order k, where k is the length of the word, because you always have to go to the end of that word to insert it into the trie. It kind of makes sense. Like when I inserted muffin, I can't just stop at I and say that word's in there now, can I? I have to go all the way to the end and say that word's in there now, put a 1 there. So insertion is always order k, where k is the length of the word. Lookup and deletion are a little bit better because their best case is order 1, even though their worst case is order k. And I would say that their average case is also probably order k. Once again, depending on how you keep your trie set up. So the reason for that, I'll actually write. The reason for that is, let's say we have muffin, and let's say we want to look up muffin, or let's say we want to look up mulligan, right? So we go to U, and we check to see if that L is there, right? And we see that L's not there, so we can just automatically now break out, because we know that that L's not there, because that L is null. And so we can't go down that path anyway. There's nothing down there. So we can just go ahead and break out, and we'd say it's an order 1 operation because we didn't get to the end of the word, and we just broke out early. Same thing for deletion. If we say we want to delete mulligan from this trie, and that L doesn't end up being there, we can say, okay, well, this word's not in the trie. We don't have to delete it. We can just break out. And those are both, you can say that those are order 1 operations. You wouldn't be able to say that if there was nothing in the trie. So there has to be at least something in the trie. That's going back to that you have arbitrarily large data. So there has to be something in there, but it doesn't necessarily have to, like, it didn't have to have that M even. We could have had like a K word in here that led to something, and then we could say, okay, we're going to try to delete mulligan, and that M's not there, so it's an order 1 operation, nothing's there. Alright, that's tries. So we're going to do some hash table stuff now. Hash tables can be pretty cool. So I asked what kind of length we like our hash table to be. And the hash table length we want that to be prime. And that's because prime numbers work out better, because when we insert into a hash table, what we're going to do is we're going to mod by the table length. And when we mod by the table length, if we have a prime number table length, that's going to give us a better spread of data in the actual hash table. And I also asked, when we expand a hash table, we usually want to expand a hash table when a hash table is about half full, because once we get to about half full, if we keep inserting stuff into it, our collision rate is going to start going up and up and up. So we will expand at half full. And can anybody tell me what the runtime to expand a hash table is? Just in any case. No? It's pretty intuitive. In order to expand a hash table, we have to create an entirely new table that's longer, and then we have to rehash all of that data, because now when we got that hash key, so let's say our hash key was like 17, and we modded by the table length. Let's say our table length is 9, so we modded by 9, right? So we got a remainder, and our remainder here is 8. So this goes in index 8. Now let's say that our hash key is still 17, but our table length has gone up to 11. And I know 9 is not prime, but I was just using that as an example. So if we mod 17 by 11 now, which is our new table length, it's going to go into a different index, because 17 mod 11 is equal to 6. So if we just copied that data back over, and we tried looking for 17 at its original index 8, we're not going to be able to find it, because we're going to be looking at 6 instead. So we have to rehash all of that data again, which ends up being an order n operation. So expanding a hash table is pretty expensive, because you have to create that table, which is already an order n operation, and then you have to rehash all of the data, which is another order n operation. So we don't like to have to expand the hash table. All right. Now, we had 3 different types of probing techniques for hash tables. And those 3 types of probing were linear, quadratic, quadratic, and separate chaining. And each of these has fallbacks, things that don't work exactly correctly. So with linear probing, our table length could be basically anything. If we're using quadratic probing, you'll see if the table length isn't prime, then we can get into infinite recursion, or infinite lookup basically. We're just looping around looking at the same values, but we never find anything. With separate chaining, we can get that problem where we have a chain that's just n objects. So if we have a bad hash function, we'll basically have a linked list. And linear has that problem where you can basically probe all the way through and you have an order n lookup. And you also have another problem with linear, but I'll go over that in a second. So I'm going to go ahead and create a hash table, and I'm going to hash a few things really quick. With no particular hash function, I'm just going to put stuff in here so I can show the probing techniques. So I'm going to put maybe like 27 here and 8 here. And then I'm going to hash something else. So let's say 27 hashed to position 2, 8 hashed to position 5, and let's say 18 hashed to position 2 as well. So now we're going to put 8, we're going to go to 27, and we're going to use linear probing. So we're going to look at the next position, which is empty. We're going to put 18 there. Then we're going to try to hash something else. Say 20. Let's say that also goes to 2. And so we're going to look at 27. We're going to keep going until we find an empty position. And we're going to put that there. Now, we're going to delete something. We're going to delete 18. So we're going to use that hash value to go to 2. And we're going to see the 27 in there. That's not 18. Then we're going to go to this, and we're going to see, okay, 18's there. So we're going to remove that and put something like maybe a -1 there to say that nothing's there. But let's say we didn't have that -1 there. Let's say that we just had all of these filled with 0 initially. And so we think that 0 is an actual value. So we deleted 18, and we basically still have a 0 here. And so we try to hash, let's say 16. Let's say that also hashes to 2. So we go to 27. Well, actually, let's not do that yet. Let's try to do something else first. Let's try to delete 20 from this. So we're going to go to 2 here, where it hashed to initially. And then we're going to advance to 3. And we're going to see, okay, that's an empty spot. So we're going to stop searching, right? Because there's nothing there. So we got to the end. Now, 20 is still in there. But we don't know that because here, we basically just deleted 18, and we didn't say that there's more stuff to the right of it. So the way we solve that is we have to have some kind of flag that can go in that position that tells us, okay, maybe we use -1. That tells us there was something to the right of this, keep going to search for it. So now we go and we go to 20, okay, that goes to position 2. Then we go to 3, okay, there's something to the right of this, so we'll keep going. And then we find 20 and we delete that and replace that with our flag. Now the problem with doing this obviously is that we lose the value -1. We can't use the value -1 here. So what you might have to have is a struct that contains the value and then a flag that says that there's something there. That might be a little bit more efficient if you need to use negative numbers. Otherwise, I think that this is more space efficient because you don't have a flag for every number on here. Yep. What is that? Why can't it just be null? Okay, so I was just assuming that this is an integer array. Now, you could make all of these pointers, and you could say, okay, well, we'll initialize the memory in this space when we get to it. So basically, initially, all of these would just be pointers that are just null, right? And then we would come to it, and we'd hash something to 2, and so we would create the space there for an integer, and then we'd go to 3, and where we put that 18 in there, we'd malloc the space for that, and then when we got here, we'd malloc the space for this. And then we could delete 18, but we would still have that, we'd still know it wasn't null, and we could keep going because we know it's not null. You could do something like that. It's a little bit more difficult because you have to keep track of memory as well. With a statically declared array, it's obviously going to be, this is the only way you're going to be able to deal with it is to have a flag or some sort. But you could also check to see if it's null. That was good. Thank you. All right, so the next one right, so what I was doing there was I was making sure that this table length was prime because I'm going to do quadratic probing. And with quadratic probing, you want your table length to be prime, otherwise, like I said, you can infinitely keep searching for something. So I'm going to insert 5, and we'll say that hashes to position 3. And I'm going to hash 7, and we'll say that that hashes position 3 as well. And so we'll go to position 3, we'll see something's there, and the equation that we use is basically the index plus that number of times that we've had to move squared. So we're just going to have to move one position. So we start with 0 basically here. So we'll say 3 plus 0, okay, there's something there. 3 plus 1, so 1 squared is 1. We'll say, okay, go to position 4, see if anything's there. And there's not, so we'll put the 7 there. And let's say we hash 19 next, and that also goes to 3. Now we're going to go 3 plus 0, something's there. 3 plus 1, something's there. Then we'll go 3 plus 2 squared, so 3 plus 4. We're going to go 7, and this one wraps around. So you'd have to make sure that you could wrap around circularly around your array. So we'd basically go 1, 2, 3, 4, 5, 6, 7. And that's back to 3, so we already checked that. So we'll have to do this again. That's actually weird. That doesn't usually happen with prime table length. So we're going to do 3 next. So 3 squared is 9. So 9 plus 3 is 12. So we'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we'll look at 1. So we're going to put that there. And that's how you do quadratic chaining, or quadratic probing. Quadratic probing, you don't need to do that thing where you check to see if something was there or not, really. Because you're always just going to keep going until you find an empty spot. And if you're searching for something, then yeah, you would probably want to have that flag still that says something was here. Because you'd run into that same problem where something might have been there before, but now it's not there anymore. All right, so the next one is pretty easy. Separate chaining, basically what happens is all of these positions are just linked lists, and linked lists might be complicated to code up, but they're not that difficult to visualize. So if we hash something like 16 to 4, then we would just create a linked list that now has 16 in it. Let's say we hash 7 to 4 as well. We have a linked list with 16 and 7 in it. And you can decide whether you want to hash things at the head or the tail of the linked list. That's kind of up to you. But searching through a linked list, that's going to kind of influence your searching through a linked list, right? So if I insert something at the tail, and it's more likely that I'm going to look up data that was recently put in to this hash table, then I'm going to want to I'm going to want to insert at the head, because we're going to start looking at the head. So it kind of depends on how recently you're going to access this data. You might want to insert at the head or insert at the tail. The head would probably be best though, because you're usually going to be accessing data that was recently put into the hash table. And so most implementations will probably insert the head instead of the tail like I did. And the same thing for searching. We'll just go, we'll look up 7 hash to 4, we'll look here and we'll continue going through the linked list until we find it or until we hit null. So hash tables are a little bit crazy. If we have an efficient hash table, I asked what the average case lookup was. And if you have an efficient hash table, the data is spread out and you're not having to probe a lot, then you should have an order 1 lookup and an order 1 insertion and order 1 deletion. All of those should be order 1 if you have an efficient hash table. All right. Now we're going to take a little break from data and do some math. And I know we all love math. So I'm going to do some base conversion stuff. So I'm going to convert 24 base 10 to base 2. And what we do when we're converting from base 10 to some other base is we basically divide by that base, find the remainder, and add that remainder on. And that'll tell us what our final number in that base is. So I'm going to do 24 equals 2 times 12, right, plus 0, because there's a remainder of 0. I'm going to take this number, and I'm going to divide that by 2 as well. So 12 is 2 times 6, plus 0. 6 is 2 times 3, plus 0. And 3 is 2 times 1, plus 1. And that kind of makes sense because converting to base 2, all you have to really look at here is whether this is an even or odd number. If this is an even number, it's going to divide evenly, and you're going to have a 0 here. If this is an odd number, then you're going to have a 1 here, and it's not going to divide evenly. So once again, we'll have a 1 here. This is an odd number, so I'm expecting a 1 remainder. So 2 times 0 plus 1. And this is your binary number, and you read it from the bottom up. So if I copy this down, that's how I would write that. Yeah. So what she was saying is if you already know what 24 is in binary, you know, because it's basically just the 2 highest powers of 2, or the highest powers of 2 you can add. So this is just 16 plus 8, which is 2 to the 4th plus 2 to the 3rd, which is what we have here. If you know that, you could probably just say that it's 2 to the 3rd plus 2 to the 4th. But, I mean, when you're trying to show your work, so especially for your final, I would show all of this because they want to know how you got through that. And especially because not all of your problems are going to be in base 2. So like say base 3, like off the top of your head, you probably can't tell me what like 37 is in base 3. But you might be able to do that with base 2. I would say that it would be important to know this process just because you're not always going to be given base 2. And even if you are, they want to know how you got there, really. But that's a good question. Obviously, for small numbers, if you're just like trying to say like what this number is, and that's all you need to do, then you can just, yeah, if you know what that number is, just write it down. But for the test, I would show the entire process. All right, so this one is going to be going from binary back to decimal. And what we do here is basically what she was talking about. We're just going to do that 2 to the power of whatever index we're at. So we start with the right. This we say is like index 0, so this is going to be 2 to the 0. And anywhere we have a 1, we're basically just going to add that. So, and for other bases, you would do basically the same thing. So if this were base 3, you might have something that was like, might have like 22 in base 3, right? Now, this isn't just 3 to the 0 anymore. This is 2 times 3 to the 0. So I just dropped that 1 here because it's kind of irrelevant. But the full equation is basically that number that's in that position times the base to the power of the index. That's the generalized form. So if you have another base, that's kind of the generalized thing. This is coming from this. This is coming from the base. And this is coming from that 0 up there. That's where those numbers are coming from. All right, so I'm just going to calculate this. So we have a 0, 1, 2, 3, 4, 5, 6. And 2 to the 6th is 64, plus 2 to the 3rd is 8, plus 2 to the 0 is 1. That ends up being 73 in base 10. Good. All right. One more, because this is a good trick to know. Going from octal or hexadecimal back to base 2, basically we're going to take each of these numbers and split them into bytes of the length that could hold that number. So we need 4 bytes to hold the number 15. And we need 3 bytes to hold the number 8. So if we were going from octal, we would need sets of 3 bits. If we're going from hexadecimal, we need sets of 4 bits. If we're going from something like base 32 to base 2, we would use sets of 5 bits, and so on and so forth. So we look at C, and the number in base 16 that is, I'm just going to write in decimal form because it's a little bit easier to convert. These are the numbers. So 12 in base 2 is this. 10 in base 2 is this. 9 in base 2 is this. And 8 in base 2 is this. And this final number is your base 16 to base 2 conversion. So this number in base 2 is something like really large. I don't know what this is, but it's pretty simple. You just have sets of 4 that you put together, and that makes the final number. So that's a really good trick to know because you'll probably see that either on the final or the foundation exam. Hint, hint. All right, so that's it for base conversion that I had. And then I have some bitwise operator stuff. So there's 4 main bitwise operators. We have the bitwise AND, the bitwise OR, bitwise XOR, and the negate. These 3 are binary. They require 2 operands. This one is unary. It requires 1 operand. If we have a set of binary, and we want to use these operators on it, So I'm just going to AND these two numbers basically. Pretend that's an AND symbol, I'm so sorry. Can't draw them. So if we want to AND these two numbers, then we look at the numbers, and basically with AND, bitwise AND, we're going to look at those two binary numbers, and if they're not both 1, then the result is going to be what we say deasserted. I want you to be familiar with that language. Asserted is 1, and deasserted is 0. So if they aren't both 1, then the result's going to be deasserted. Otherwise, if they're both 1, it's asserted. So that's the only condition you're looking for here. So it's going to be 0, 0, 0. These are both asserted, so the result's asserted. These are both asserted. And those are both asserted. With bitwise OR, we're going to have the result asserted if either of the operand bits is asserted. So as long as one of them is 1, you can think of it that way. As long as one of them is 1, the result's going to be a 1. So this one's going to be 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1. Now, the XOR is a little bit different. Exclusive OR is only asserted if only one of the operand bits is asserted. If both of them are asserted, or if both of them are deasserted, the resulting bit is deasserted. So we're going to look at this. Only one of these is asserted, so it's going to be a 1. Same thing with the next one, same thing with the next one. But we see both of these bits are asserted, and so the resulting bit's going to be a 0. And the same thing with all 4 of these, because for all 4 of these bits, they're both either 0 or 1. And so that would be the result there. And the negate, I asked to negate that second number. So that second number, if we negate it, and we just negate it, if we negate a number, what we're expecting to get is the negative of that number. Now, negate doesn't necessarily know that, and so when we do this actually in the CPU will handle it. But here, since I haven't given you the full 32 bits, you don't know that if you just invert these bits, which is what the bitwise negate is, you're not going to get the right answer technically. So if I negate the second number here, this is what you would get. And that is positive like we would expect it to be. And if we negate the first number, that's negative like we would expect it to be. But if there are more bits here, let's say that these were all padded with 0, that first number is going to be all right, but the second number is now wrong because it's still negative, because we inverted that bit which was there, but we didn't know it was there. And so when you invert, the computer, the CPU will know to do some math magic on that to make this the positive number that you expected. But when you're doing this by hand, just remember that to add, like if they say that this is an 8-bit number, then add another bit to the left to see what's actually going on. Otherwise, you might get the wrong answer. All right, so one more thing with Bitwise is shifting. So this is a shift right, this is a shift left. And basically takes one operand. This basically just means shift this number left by 3. And when we're shifting left, we just always pad in zeros. So we're going to shift this by 3, and we're going to end up getting actually that's 2. We're going to end up getting that. But if we shift right by 3, then we have to take into account whether this is an arithmetic or logical shift. With arithmetic, we pad with the most significant bit, and with logical, we always pad with 0. So in this case, it doesn't matter because most significant bit is 0. But if we had a number like this, and we wanted to shift right by 3, we would have to pad the left with 1s. So this would be that if it was arithmetic. And it would be this if it was logical. So be aware of those different kinds of shifts. If the number is signed, then I would assume that it's going to be arithmetic, because the reason that we do an arithmetic shift is to keep the sign, because otherwise when we shift it's going to become a positive number if it had a 1 there. So that's the reason we do arithmetic shifts. So if it's signed, I would assume it's arithmetic. If it's unsigned, I would assume, well, I mean, it doesn't really matter if it's unsigned. You can do logical or arithmetic. It doesn't really matter at that point. Well, actually, it does. But with unsigned, you're probably always going to do arithmetic if you're doing arithmetic operations still anyway. So it just kind of depends on what you're doing, not necessarily on the type of. Okay, so we usually work with 2's complement numbers, and with 2's complement numbers, the way you get the negative of a number. So let's say this is a positive number in base 2. The way we get the negative representation is by inverting all of the bits and then adding 1. So this would be the negative representation of that number. Now, in 2's complement, this bit tells you whether it's negative or positive, the most significant bit. Now, when we do an arithmetic shift, you keep that bit intact, basically. It still tells you information about, is this number positive or negative? And that's why we do the arithmetic shift. But I would say that you're not going to do a logical shift just because it's unsigned. Usually with a language, especially with like C, it's always going to be an arithmetic shift or it's always going to be a logical shift. You're not going to be flipping back and forth. A logical shift is usually going to be used when you don't care about the math that's happening, which isn't very often. It's usually going to be an arithmetic shift. But I think you would be told what kind of shift it's going to be. All right. I have a short section here for backtracking. I'm not going to go over it too much because I think that most of what you need to know is just the foundation of a backtracking algorithm. And a backtracking algorithm is recursive. So you're going to have those same requirements that a recursive function will have. You're going to need to have that base case, and then you're going to have probably some kind of loop. And within that loop, you're going to have your move that you make. So you're going to manipulate your input data. We could say that. Then you're going to make your recursive call. And then you're going to reset. And basically what this means is reset data to before the loop. So you'll reset that data to before you came in so you can make your next move. And then depending, this might not be a recursive call here that returns. So if this returns here, just like with any recursive function, if this returns here, then you're not going to get down to your reset. And so you might not have to reset anything. You might just return here. But otherwise, you might have a value assigned to the recursive call. And then you do your reset, and then your return is at the bottom. So that kind of depends on the type of recursive function that this is. You might either return up here if you don't have to reset anything, and if you don't have a loop. But that's not going to happen very often. More often, you'll have some kind of variable that you assign to that recursive call, and then you'll return that down here somewhere. But this is the basic structure of a backtracking algorithm. And I would say you definitely need to know this. This is going to be really important, both for the final and possibly the foundation exam, but you'll definitely see this stuff again. So you have a few problems I think you guys have seen. I'm not going to draw the entire thing out, but you've seen the maze, where you basically start somewhere and then you go down a path, and then you go down this path, let's say, first, and we stop there because we can't go anywhere else, and then we start recursively calling our way back up until we hit a place where we can make another move. And so then we go left, and we just continue going this way now until we hit an exit or something. That's basically what a backtracking algorithm is. You go all the way down one path, and then you return back up, and then you go down another path, and you return back up. Backtracking algorithms can, so the backtracking algorithm isn't necessarily related to any specific data structure. Like what I just did with the maze, that would be like a two-dimensional array where you're in the maze, you're trying to see which direction you can go, and you're picking a direction. Now, you can also have a backtracking algorithm with a binary search tree where you go all the way down one segment of the tree, and then you recursively go back up and go down another segment of the tree. So that's like when we were doing the pre-order traversal, right? I would say that that's technically backtracking because we went all the way down to the left, we printed it out, and then we went back up, and then we went to the right, right? So I'd say that's kind of backtracking. You could see backtracking with basically any data structure, I'd say. It's not really about the data structure, it's about that structure of the algorithm that I showed you, where you have the move that you make, the recursive call, and then the reset for the move. For the maze, you'd have some kind of if condition up here, and then you'd have a for I through whatever, and then a 4j through whatever. So this would go through your two-dimensional array. Now, these would actually be like your directions. So you would try going up and then right and then down and then left. And so in here you would say that your next move, so your next x that you're going to go to, is your current x plus like some direction. And then your next y is equal to your current y plus some direction. And then you would make the recursive call. So let's call it maze. With your new x and your new y. So that's the new position you're going to. And then this one doesn't even really need to be reset because you're not really manipulating anything. But if it needed to be, then we would do our reset down here and we'd set that back equal to 0. But these aren't really necessary. And at the bottom you'd have like your return based on what happened in the loop. So that's kind of what it would look like. With a two-dimensional array, you're not like calling the recursive call on like every single position, just positions that you can go to. And so it doesn't really get out of hand because you'll have a big conditional here. So you're like, there'd be a conditional that say, okay, we can make this move, this isn't out of bounds, stuff like that, right? And that's kind of what restricts you, so that you're not making like tons of recursive calls. You're welcome. And you also have that n queens problem that you might have seen. How many boards of size whatever, or how many, yeah, so how many chessboards with queens on it of size whatever, so this would be n equals 5. How many of those boards can we create that would have queens that can't attack each other? And so you just start putting a queen down. So you'd put one down in the first position, then recursively call the next column, and we'd put one there. So we try putting one there. Well, those two can attack each other. Then we try putting one here. Those two can attack each other. And then we get down here, and we'd see that they can't attack each other. And we keep doing this until we got to the final column, and we saw that none of them could attack each other there. And then we would recursively call all the way back up. We would check the final position first, obviously, but then we would eventually get back to this first position. We'd reset it, go to the next square down, and then we'd do the same thing. We would go to the second column, check that, they can attack each other, check that, they can attack each other still, until you eventually got down here and they can't attack each other, and you recursively call for the next column as well, and keep going basically. So that's kind of the recursive reset thing, where you come back up, you take another path. Does that make sense? So if we kept going, we'd start here, and then keep going down until we found a position where it can't be attacked, which it's already in one. And so we'd call it on the next one, the next column, and go there. And this board, I don't think this queen in this first position can actually work on this board, but you come back and then do that. That's a backtracking algorithm. That's it for the most recent stuff. So for those of you that don't have a cumulative exam, and for those of you that have cumulative exam, that's probably going to be like most of the big stuff on your exam. So is everybody all right with all of that? If you have questions on any of that stuff, now is the time to ask. So that was binary search trees, hash tables. I didn't go over heaps, so I guess I could go over heaps real quick. Heaps, so you have two different types of heaps. You have min heaps and max heaps. Min heaps always keep the smallest value at the top, and max heaps always keep the largest value at the top. So if we have a min heap, let's say it looks like this. That wouldn't work. Say we have a min heap like this, and we want, well actually let's add one more layer so this makes a little more sense. So the ordering property for heaps is that everything below a node is always less than, or is always greater than that node. And actually, let's remove this. It's always complete, which, if you remember that definition from before, it's always filled in from left to right. And we do that because when we delete stuff, that makes it a lot easier. And when you're deleting stuff from a heap, you always delete that's the only thing you can delete. You can only delete the minimum node. You can't like delete stuff from the middle of the heap because you can't really find it. So if we have this heap and we want to delete 2, what we do is we grab the thing that's furthest to the right, so like the last thing that we inserted basically, and we put it at the top, and then we percolate down, is what we say. So we choose the smallest number to either the left or the right of 9, which is 7, and we put that there. And now both of the numbers below 9 are greater than it, so we're good. We don't have to move it any further. Now let's say we wanted to insert something like 5. We would insert it, and then if it is less than the number above it, so if it's less than its parent, we're going to percolate up, is what we would say. We're going to swap it as long as the parent is less than it. So 5 was less than 8, we moved it up, and 5 is less than 7, so we're going to move it up. And that keeps that ordering property of the heap. So I kind of forgot to add heaps to this review guide, but they're really similar to binary search trees. They just have that different structural property where they're always complete, and the different ordering property where every node, the things that are below that node are always less than it. All right, so with that out of the way, I'll start going over stuff from like the first half of the semester, and we'll just try to get as far as we can. I'm going to just do a brief overview of all this stuff. So first, with memory allocation, we saw 3 different functions that can allocate memory. Malloc, calloc, and realloc. Malloc just allocates a block of memory. Calloc allocates a block of memory and zeroes it out. And if it's pointers, then it treats them all as null. Realloc takes a pointer to the original array and the new size that you want, and it creates that new size array. So malloc the only argument to malloc is that size of the block, which is why we do size of int times the number of elements. That gives us the size of the block that we want. Calloc takes the number of elements and then the size of each of those elements. So you would put like 10 here and then size of int here if you wanted 10 integers. Realloc takes that array pointer or whatever you have. You might just have a structure that you want to resize, but this takes the pointer to whatever you're resizing And this also takes the size of the block of whatever you're resizing. So this would still be, like, let's say we had an array called, let's just say we had a string called string. We would put string there. And then if we wanted 10 characters, we would basically do that. And that would be the arguments to realloc there. All right. So that's memory allocation. And I put some stuff here. I'm just going to go over the second one because that's a little bit more difficult. As I asked to create a two-dimensional array of type node star. And that might sound a little freaky at first. But basically, count up the number of pointers you're going to need, and that's going to be the largest pointer that you're going to create. So we have a two-dimensional array, which means we need a double pointer. We need a pointer to the two-dimensional array, and we need an array of single pointers to their own individual arrays. But we also need the nodes to be pointers, which means that we need a triple pointer. We need two-dimensional array with an array of single pointers, and then those single pointers have an array of nodes which are their own pointers. So all right, kind of ran out of room there, but this is node triple star array equals malloc size of node star star times rows. And that's basically always going to be the foundation. You're going to have the number of pointers here. This number of pointers is usually going to be -1 from that. So if we have 3 here, this is going to be 2 here. That's usually how it's going to be structured. And then we'll have a loop, which we need to create that two-dimensional array. I'm going to run out of room again, but I'll read it off. So this is each array index. So this is basically the two-dimensional array we're creating. So each of these single arrays, we want to create another dimension, which is the columns. So these are the rows that we're going through, which you can see by the loop index. So we're going to go through array I. We're going to malloc size node star. That's the array. So we have an array of type node star. And we're going to multiply it by the number of columns that we have. So now we have a two-dimensional array of type node star. So we need another loop, which we can just put inside of this loop. And basically the thing at that index, so we're basically going through the number of columns here. So for that array, or that row that we just filled in with columns, we're going to create each of those nodes here. So that's a kind of crazy memory allocation problem, but I did that because this kind of shows you like how you can think of pointers, because it deals with a lot of them. So you have that triple pointer up here, which kind of seems scary at first, but if you look at it, this just means we have a two-dimensional array of type node star. And in fact, this could have been a three-dimensional array. I could have made this a three-dimensional array. I would have done that down here. Instead of doing size of node, I could have multiplied that by something and created a three-dimensional array instead. But I decided to make this a pointer to the struct instead of a three-dimensional array. So pointers are just how you declare them. Is everybody good with that? I'm going to take a poll since we're running out of time. Raise your hand if you want to go over runtime analysis, so recurrence relations, stuff like that. Okay, I think we have enough people that we should probably do that. Okay, so I have a pretty beefy recurrence relation here. And I've asked to solve it by iterative substitution. And I'll also put the initial condition here. Actually, that was 0. So this is a pretty long problem, so it's probably going to take most of the rest of the time. But basically with iterative substitution, we look at that thing that's in our equation, and we want to solve for that. So we're going to plug in n over 2 anywhere in this original equation. We see an n, basically. So we're going to get n over 2, which is n over 4, plus n over 2 times 3, which is n over 6, plus 1. Then we'll do n over 4. And then we'll also do n over 8, because this pattern's a little bit difficult to see. And now we're just going to plug in. And I'm going to skip all of the plugging in, but basically what you do is you plug in t of n over 8 into this, and you'll get this long equation plus this. Actually, I probably should do the plugging in, because you'll see the pattern better. So I'm going to go ahead and do this in one step, but this is n over 24 plus n over 12. So it's going to be 2n over 12 plus n over 24, or 2n over 24 plus n over 24. And this divides 24, but I'm going to leave it because you should probably leave things when you do iterative substitution. It just makes it a lot easier, because what you're looking for at the end is a pattern. And if you simplify stuff, you're going to lose that pattern. So I would leave things unsimplified, because that pattern's not going to show itself if you try to simplify stuff. So this is actually plus 2, because we had 2 1s there. And this is 3n over 24 plus n over 6. That's going to be 7n over 24. Yeah, I'll move it up. And then we have 7n over 24 plus n over 3, which is 15n over 24. All right. If you need to get that down, get it down, because I'm going to have to erase it. All right, so I'm going to rewrite the base case up here. Now what we're looking for is a pattern. So we want to write that pattern in terms of something that's not n. And what we want to get in here is the base case. So that t of n over 16, we want to turn that into the base case. And 16, if you look at it in terms of the number of steps, it's basically 2 to the number of steps. So we did 4 steps to get to this 16, which means that it's going to be about 2 to the 4th. Well, it is going to be 2 to the 4th. So if we rewrite that in terms of k, where k is the number of steps, we want that to equal n so that we can get our base case. So we're going to rewrite this. Now this is the complicated part. 15 doesn't look like a power of 2 or anything like that. And if you remember what I was doing when I said don't simplify any of that stuff, I actually made the mistake of simplifying all that stuff. I simplified the numerator because when I kept adding that stuff, I kept like multiplying the numerator by a number to get the same denominator. And what was actually happening there was I was summing up all of the numerators, and that equation was basically the sum from I equals 0, from I equals 1 to k of 2 to the k, all over 3 times 2 to the k. So that 24 came from here. It was 3 times 2 to the 4th, which is 24. And the summation will work out in a second. Don't worry about summations if you have them in your recurrence relation. Just kind of leave them there and then come back and work with them after you finish this. This is basically plus k at the end there. So I'm going to go back and I'm going to solve this summation really quick. So this also gives you a little experience with summations as well. So when we have geometric sums, there's a little trick we can do. And if you have Zumlansky, you've definitely seen this. If you don't have Zumlansky, then you might have seen this, I don't know. But basically the trick is you write out the series. So this is going from 2 to the first to 2 to the k. And we call that series S. And then we multiply that S by the base, basically. So we multiply that S by 2. And what's going to happen is it's going to increase all of those powers by 1. So 2S is 2 squared, so that 2 to the first plus 1, all the way up to 2 to the k plus 1. Because 2 to the k plus 1 is basically 2 to the k times 2, because you add those exponents. So now if we subtract these, 2s minus s will give us s, basically. And we basically look at, okay, what's this series minus this series? 2 squared is in this one, and so we subtract everything from 2 squared onwards. And 2 to the k plus 1 is in this one, so we subtract everything up to 2 to the k, and we have a 2 to the k plus 1 remaining. So if we do 2s minus s, what we're going to get is we're going to get 2 to the k plus 1 minus 2 to the first, basically. And that's that trick you can do. If you write out the series, multiply it by the base, subtract them out, you'll always get some kind of representation, some kind of form that you can actually use. So I'm going to rewrite this in terms of that. And then I want this 2 to the k to equal n, so I'm just going to write that. 2 to the k equals n. And vice versa, k equals log of n, because we'll need that too. So I'm going to plug in an n anywhere I see 2 to the k, and I'm going to plug in a log of n anywhere I see a k, or yeah, an n anywhere I see a 2 to the k, a log n anywhere I see a k. So this is going to be d of n over n, which is just 1, so that's our base case, plus 2 to the k plus 1. This is just 2 times 2 to the k, so that's 2 times n, minus 2 over 3 times n, so that's another 2 to the k, plus log of n, because our k is equal to log of n. And we found that by just taking the log of both sides there. More specifically, it's the log base 2 of n. I just dropped that though, so we won't need it. Now, if we simplify this, what we end up getting this. And so if this was our recurrence relation, and we're looking for the runtime out of this, we have a constant, which is pretty large in this case, actually. Well, actually, it's not large. It's really small. So it's not going to be our upper bound. And then we have an inverse n here, which is pretty small, but it's still on the order of n. And so that's not our runtime. And we have a log n, which is it's our smallest, it's the largest of our numbers here, basically. So as n gets larger, this is the largest thing that we're going to have. And so our order would be log n for this one. And that comes from that initial thing where it was t of n over 2. Usually when you have something that's divided by something, you're going to have a logarithmic runtime. And in fact, in this case, you didn't even have to do that summation because that didn't end up being your largest value. But it could have been. And so that's why I kind of put it in here, because sometimes you'll see stuff like that where the number doesn't really make any sense. Like you can't see, like, what is this? It's not 2 to the k, so I don't know what else could it be. Sometimes it might be a summation. And I wouldn't get scared if you see something like that. Just kind of go back, work through it, and see, like, what was I doing to get to this step? And then if you get to that step, you should kind of know where you came from. Like I added these things or I multiplied these things. All right. So we did some summation stuff there. Other important stuff, because I don't really have time to go over it. I would know all of your sorting algorithms. I would know, in fact, I can bring up really quick okay, I didn't have that on there. Okay, well, I would know your sorting algorithms. So insertion sort, selection sort, bubble sort, merge sort, quick sort, bucket sort, and radix sort. And I would know all of them, how they work. I would probably know how to code up your n squared sorts, so bubble, selection, insertion. But at least be able to trace through merge, quick, radix, and bucket. Be able to use a stack to convert from postfix to infix and infix to postfix. If you know how to do that, then you know how to use a stack. So that'll cover both stacks and infix and postfix notation. There's some questions for that on the foundation exams. So all that was really left was recursion. stacks and queues and linked lists. Now linked lists is probably the hardest part of those. I would look over how to insert into linked lists if you don't have a tail pointer. So how to insert at the head, the tail, without a tail pointer. How to insert in a linked list if you have a tail pointer. How to delete from a linked list, possibly. I know I wrote down something on here like try to sort a linked list, because for those of you that have a cumulative exam, I don't know, you might be asked to do something with a linked list that's kind of something you haven't really seen before, like reverse this linked list or sort it or something like that. So I would look at stuff like that. Breadth first search. So does anybody know how to go through a binary search tree with breadth first search? You do? With breadth first search, basically what you do is you add things onto the queue. So I'm just going to do this. So we would enqueue 59, and then we would dequeue it. So this is in the queue, we dequeue it, and we enqueue both of its children. And then we would go to the first thing in the queue, which is 25. We would dequeue that, and enqueue its children if it had any. And then we would dequeue 72 and enqueue any of its children if it had any. And that will let you go from left to right through the binary search tree, or the tree, whatever it is. You can do that with mazes too, so that depth first I showed you for mazes, you can also do breadth first, and breadth first will allow you to find the shortest exit in a maze, because you'll basically enqueue all of the positions around the one you're currently at, go to them, enqueue all of their surrounding positions, and then dequeue them. I think that was basically it. So are there any final questions? Anything. It could be on anything. All right. Well, in that case, if you didn't get one of these, please raise your hand. So I want you to fill them out really quick before you leave. And those of you that already got one, I'm going to come by and collect them.
Thanks.
And just keep your hand raised. All right. So that concludes the session, I guess. How are you guys feeling about the exam right now? Yes? No? Just trying to get the temperature in the room.